Welcome to a screencast on an introduction to solutions and electrolytes. The objectives are to describe the basic components of solutions and how and why solutions form, and to define and give examples of electrolytes and distinguish between strong, weak, and non-electrolytes. Now, in your daily life, you run across solutions all the time. Most things you drink are probably solutions, so you might have some Gatorade, you might have some coffee, you might take some cough syrup, or if you're not fortunate, you might end up needing some medical treatment and maybe have an IV. All of these are examples of solutions. In general, a solution consists of a solute that's dissolved in a solvent. So the solution is the whole thing. The solute is typically the substance that is in the smaller quantity, and the solvent is typically the substance that is in the larger quantity. And as a note, the solvent in many cases for us, a universal solvent, is of course water. Now, technically, to be a solution, the solute particles have to be small enough. So to be a solution, the solute particles need to be the size of typical ions or typical small molecules. If the particles are too big, you might still have a mixture, but it's not technically a solution at that point. Here's a sort of schematic picture of a solution. The sort of reddish spheres represent solute particles. Those are in smaller quantity or a smaller amount. The blue background represents the solvent. In this case, it's water, but it could be something else. I'm not showing any individual molecules, but there are more of them, and that's sort of just a schematic version, idealized, simplified version of a solution. If we looked at a solution on a molecular level, here's a real solution, lactated Ringer's solution. And if we look at this on a molecular level, this Ringer's solution consists of some potassium chloride and some sodium lactate and a few other things that are dissolved in the solution. Here we're just showing the potassium chloride, and the potassium chloride actually dissociates into potassium ions and chloride ions, represented by purple spheres and green spheres respectively. And then the sodium lactate. Lactate is the conjugate base of lactic acid. I'm actually showing here some lactic acid molecules just to give the basic idea of what's going on. And we have some of those dissolved as well. All of these are surrounded by lots and lots of water. I'm not showing most of the water here, but just some representative water molecules around the solute particles to just give an idea of what's going on. And important thing to note, potassium ions are positively charged. Water molecules have a side, the oxygen part of the water molecule, that's a little bit more negatively charged, and then the hydrogen side of the molecule is a little more positively charged. These are what are known as polar molecules. And around the potassium ion, the negative side of the water molecule is nearby and attracts to it. Around the chloride ions, the exact opposite happens. Chloride is negative, and so the positive side of the water molecules attract to that. And these attractions are what actually make the sodium chloride dissolve and dissociate in solution. And then similarly with the lactic acid molecules, the oxygen in lactic acid, red sphere here, is a little more negatively charged. The hydrogens, the sort of grayish spheres, are a little more positively charged. And so the oxygens in lactic acid are attracted to the hydrogen in water molecule. The hydrogen in lactic acid is attracted to the water. And again, these sorts of attractions are what allow the lactic acid or the lactate to dissolve in solution. And in fact, this is what is going on to make things dissolve. If the types of attractions between the solute and the solvent particles are similar, so here we have some red solute particles and some blue solvent particles, if they have similar types of attractions, intermolecular attractions, then that's likely to make a solution. And you may have heard a very simplified version of this before, which is that like dissolves like. And so like in this context means similar or like intermolecular forces. And what it means is that polar substances or ionic substances tend to dissolve in each other. They have charges, and nonpolar substances tend to dissolve in nonpolar substances, but polar and nonpolar don't dissolve in each other very well. And the classic example is oil, which is nonpolar, doesn't dissolve very well in water, which is polar. Now, one more thing to note: when solutions are formed and they make ions in solution, we call these things electrolytes. This is because ions have charges, and electrolytes are things that allow conduction of charge. And if you hook up what's called a conductivity apparatus or a conductivity meter, this is one version of it. It's a light bulb. Plug it into a power supply, and then you have an incomplete circuit. You have a wire and that doesn't connect to, this part of the wire does not connect to each other. But if you put this disconnected wire in a solution that contains some positive and negative ions, those ions will flow. They'll complete the circuit. They will allow the light bulb to light quite brightly. And this is what is called a strong electrolyte. It does a good job of letting the light bulb light, and it's because there's lots of ions in solution. Now, we can have a situation where there are some ions in solution. Here's a negative particle, here's a positive particle, but there's a lot of substance that doesn't form positive and negative ions. And in this case, there is a little bit of charged particle that can complete the circuit and allow the light bulb to light. It lights dimly on our conductivity apparatus, and we call this a weak electrolyte. It doesn't do as good a job of conducting charge. And of course, if there is no charge at all in the particles that are produced in solution, there's no ions in solution, then that doesn't allow the light bulb to light, doesn't complete the circuit, and we call that a non-electrolyte. And the general classification for electrolytes into strong, weak, and non-electrolytes in terms of how you would tell what type of substance, or given type of substance, what sort of electrolyte would be. Strong electrolytes, examples of those are strong acids and ionic compounds. Both of those make lots of charged particles in solution, of course, if the ionic compound dissolves. Weak electrolytes, typical examples are weak acids and weak bases. They make small amounts of charged particles in solution. And then most molecular compounds don't make charged particles in solution, and so they would be non-electrolytes. And just a few examples then of strong electrolytes: HCl, hydrochloric acid, HNO3, nitric acid, potassium chloride, a soluble ionic compound, sodium nitrate, a soluble ionic compound. These all are strong electrolytes. Weak electrolytes are things like hydrofluoric acid, acetic acid, ammonia. Hydrofluoric acid and acetic acid are weak acids. Ammonia is a weak base. All of these only partially dissociate into ions in solution. They don't conduct electricity too well, and so they're called weak electrolytes. And then non-electrolyte examples, things like hexane, C6H14, glycerol, C3H5 and then 3OH groups, and ethanol, C2H5OH. These are all molecular compounds and non-electrolytes. And that is it for the screencast on an introduction to solutions and electrolytes.